Yeah. So good morning students. I welcome you all back onto this course Abhyas series on fluid mechanics. Okay, so right now we are in the second lecture on the concept of pressure and its measurement. Correct. So in yesterday's class we have talked about fluid and its properties basically. So we have seen some nice questions actually dealing with viscosities, bulk modulus, compressibility, surface tension, all these beautiful concepts. Okay, so in today's session, okay, so I hope I'm audible and I'm visible, right? Yes. Okay, so I hope I'm audible, correct? So please confirm. Yeah, okay. So now let us see this case. Okay, so in today's session we'll talk about pressure and its measurement. So basically we talk about the questions on this hydrostatic law and also on the concept of manometers very importantly. Okay, and whenever time comes, as I have explained you, that's few concepts in yesterday's class during solving of problems. Same in today's session also we will go through some problems. Okay, and whenever there is some necessity we will definitely talk a bit on concepts as well. Clear? So shall we start? So please type in the chat box. So please type in the chat box. Is that clear to all of you? So shall we start the session? So shall we start the session? Shall we continue? Yes? Punab? Okay, love. Fine. So let us start with this first question. So first question, the variation of pressure with respect to altitude in an isothermal compressible medium is. Okay, so let us see. Yeah, hi Amit Nishad. Good. So let us see this question. Okay, first 1-2 questions I have said some easy and of course most repetitive kind of questions, so that's why you will have some idea, basic idea. Okay, we have very good questions as well, like we have solved in yesterday's class. Okay, now let us see this. The variation of pressure with respect to altitude in an isothermal compressible medium is. So anyone with the answer? So we have seen basically in case of this hydrostatic law, your dP by dz is given by minus specific weight of the fluid. Now tell me one thing, I'll ask you one question. C is the correct answer. Okay, now I'll ask you one question. Forget about hydrostatic law. Let me ask you one simple question. Okay, there is some derivation and all, there is hydrostatic law, so which is equal to minus specific weight of the fluid. Now let me ask you one question. Let us suppose you have a free surface of air and water. For example, let us suppose you placed your hand 1 meter below the water level, left hand 1 meter below the water level, and right hand 1 meter below the air column. In left hand below the water column 1 meter below, and right hand below the air column 1 meter with air column. So tell me, in which case you feel more weight, in which hand, on which hand you feel more weight actually, left hand or right hand? On left hand there is water on the top, on right hand there is air on the top. Now tell me, what hand will experience more pressure, or which hand will experience more pressure actually? Tell me this. Which hand will experience more pressure? Tell me, out of these two hands, left or right? Obviously it's left hand, correct? Because if you see, the reason being the fluid on the left side has more specific weight. This is what we physically observe without doing the derivations of hydrostatic law and all these things. So that means if you try to understand carefully, this is the case. So if this fluid is a compressible gas, then if you assume this as an ideal gas, so P is equal to rho F RT. So here this is isothermal, so T is constant, R is constant, density of the fluid is also constant. So density of the fluid can be taken as P by RT. Okay, so density of the fluid can be taken as P by RT. So if you simplify this, dP by dz is equal to minus P by RT times G. So if you differentiate this, 1 by P dP is equal to minus G by RT times dz. So upon integration you will come to know that this P is e to the power minus gz by RT plus some constant. Okay, so that's how the pressure variation in an compressible isothermal fluid is actually exponential in nature. Okay, so now let us suppose if you have an incompressible fluid, it is linear. In case of compressible medium, it is compressible isothermal medium, it is exponential in relation, and in case of this non-isothermal compressible fluids, we have power law kind of variation. Okay, so of course here the answer is exponential. So let me give you these points. So in incompressible medium, in incompressible medium, your pressure variation is linear. In compressible isothermal medium, isothermal medium, this is exponential in nature, and in non-isothermal compressible medium, in non-isothermal compressible medium. So in non-isothermal compressible medium, your variation is power law kind variation. Okay, so this is power law kind of variation. Power law kind of variation. Correct. So this is power law kind of variation. We have seen this. Correct. Is the series for civil students also? Yes, definitely for civil students also this series is going to help you out. Okay. So first question is a simple question straight away, but obviously these three relations is somewhat important because they came in many exams, many repetitive number of times, not only in GATE in as well as other exams also. So that's why I thought of discussing this once as the first simple question. Okay. Now let us go for the second question. So second question, in a chemical reactor 100 meters tall, so there is a chemical reactor of 100 meters height. The density of the fluid mixture varies with distance z in meters above the bottom of the reactor as rho is equal to 1000 times 1 plus z by 500 plus z by 1000 whole square. Okay, so if you see there is a big chemical reactor. Normally we see a lot of reactors in chemical industries, like in HPCL also I have seen few. So if you see there is some chemical reactor like this, there is some chemical reactor. So what happens inside this? Lot of chemical reactions will happen actually. So there is some chemical reactor like this, and in this chemical reactor you have a lot of chemical reactions that takes place. Okay, now it's given the height of this chemical reactor is 100 meters. Correct. So the height of this chemical reactor is some 100 meters. 100 meters. Okay, so the height of this chemical reactor is 100 meters. Now it's given inside this chemical reactor the density of the fluid mixture varies with the distance z in meters above the bottom of the reactor as rho is equal to 1000 times of 1 plus z by 500 plus z by 1000 whole square. So if you see they have taken this z direction from this and they have measured z in this direction. So when they measured z in this direction from the bottom, they know that the density variation is basically given by density at any location z is given by this equation 1000 times of 10 cube. Let us write 10 cube times of 1 plus z by 500 plus z by 1000. Correct. So z by 1000 whole cube. Correct. So whole square, z by 1000 whole square. Okay, so this is the density of the fluid above this. So as you're increasing, let us suppose at this point corresponding to the z value you have some, this is z is measured from this reference. Okay, because they told from the bottom of the container, okay, bottom of the vessel. So as this z is increasing, the density of the fluid is also changing, because obviously let us suppose there is some chemical reactions and the density is changing like this. Okay, now they are asking you, assuming the mixture to be effectively stationary. So what is the meaning of this effectively stationary? We are assuming normally inside a reactor what happens, because of certain chemical reactions there is some motion of the chemicals, but actually here we are assuming that the substance inside this chemical reactor is almost stationary, is effectively stationary, means as a bulk if you take there is no motion for this. Okay, so this is stationary. Now whenever this is stationary, can I take this medium inside this as some static fluid? Please tell me. Inside there is some gas kind of thing. So tell me, whenever I am taking this reactor, if the fluid is effectively stationary, can I assume that this fluid is in static condition? Yes or no? So please type in the chat box. Can I take this fluid inside this is effectively stationary, means the fluid inside this is in static condition. Can I apply this? Yes, correct. So I can apply this is a static fluid. So this is a static fluid. Static fluid. Static fluid. Then what they're asking you, let us see here what they're asking you. The pressure difference between the magnitude of pressure difference between top and bottom of the reactor is dash. Of course the answer should be in kilopascals. So let us suppose here the value is P1, here the value is P2. For example, let us say they are asking this P1 minus P2 absolute difference. Okay, you know, because of the fluid column here the pressure will be more comparatively. So P1 minus P2 value is what they are asking, and they are asking you this value in kilopascals. Okay, so P1 minus P2 is dash. This is what they have given you. Okay, now how you will differentiate this? Basically means how you will determine this value. Here at this bottom we have z is equal to 0. On the top, if you see, this is a 100 meter reactor, so z is equal to 100 meters here. So let us take z1 and z2. Similarly, pressure at this location P1, pressure at this location P2. Now let us, sound is amplifying. Sound is amplifying, but okay, maybe some issue. Okay, fine. Now it's fine. Okay, so now Integrate OGH. Yes, exactly. We will do the same thing. So we know hydrostatic law gives you hydrostatic law tells you that dP by dz is equal to minus density of the fluid times gravity. Correct? This is what we have. So this minus is because, you know, as z increases in the upward direction, the pressure will keep on decreasing, and here also we have taken z in the upward direction, because here in this equation it is told that z in meters above the bottom of the reactor. So that's why this is the reference. So z again we have taken in the positive direction, so this minus sign remains as it is. Now let us do the integration. This implies dP by dz is equal to minus g times of this density of the fluid, which is 10 cube times 1 plus z by 500 plus z by 1000 whole square. Okay, so this is the case. So this implies, if you remove this dz here, if you want to shift this dz, then this dz can be written on this side of the equation. This is dz. Now one thing is very clear. If you want to integrate this between two locations, you know, at location z1, when z is equal to z1, means basically this is 0, of course, the pressure P is P1. Similarly, when z is equal to z2, which is of course 100 meters, what is this pressure? P2. That's what we want actually. Correct? This is what we want. Now using this minus sign, let us suppose if you flip this, means using this minus sign, if you shift this minus to the left hand side, then you can interchange the integrals. So this implies P1 minus P2 is equal to g times of integral 0 to 100 10 cube times of 1 plus z by 500 plus z square by, this can be written as 10 power 6, this value dz. So let us simplify carefully. If you simplify carefully, you will get the answer. Okay, so XC question always difficult than ME questions. Yes, of course. If you see in XC, the questions are of some higher level, because only 2 subjects you have to take in choice. Okay, so but if you follow the basics carefully, you will get answers for all the XC questions as well. No issues. Okay, so let us see. And definitely in this course, I am putting problems in such a way that we will definitely have some basic idea on all the XC questions. Means if you can solve these questions, you will be able to solve majority 95% of the XC questions as well. Okay, but there are certain 2-3 topics which if I touch in mechanical, it will take some time, so that's why I'm not touching that. Okay, perfect. So focus here. So this is equal to, let us see the integration, 10 cube times of z plus into integration of 1 z plus integration of z by 500, z square by 2 into 500, which means z square by 1000 plus integration of z square by 10 power 6, z cube by 3 into 10 power 6, correct? So z cube by 3 into 10 power 6 within the limits 0 to 100. This is how we have the integration value. So P1 minus P2 is equal to g into 10 cube. What is the value of g given? Nothing is given, so let us take 9.81 by default. So 9.81 times 10 cube into, now let us substitute the limits, 100 minus 0, 100 plus 100 square minus 0 square, so 100 square, which is 10 to the power 4 by 10 cube, plus when you substitute z is equal to 100, 10 square whole cube, so 10 to the power 6 minus 0 cube, that is 0 divided by 3 into 10 to the power 6. Okay, so this is the value that you have. Now 10 power 6 and 10 power 6 gets cancelled, this gives you 110. So total, if you see, this value is in pascals because we have substituted g in meters per second square and z is in meters. So if you want in kilopascals, then definitely you need to you can take off this 10 cube actually here. So if you take off this 10 cube, the answer which you're going to get is in kilopascals. Okay, so let us see, 9.81 into 100 plus 10, 110 plus 1 by 3. So 110 plus 1 by 3, these many kilopascals is what you have here. Okay, so let us simplify this relation. 9.81, let us take a gate calculator, virtual calculator, and let us try to solve this. So if you see, 9.110 plus 1 by 3, 110 plus 1 by 3, so this is what you have, multiply it with 9.81. so if you see, 1082.37, 1082.37 kilopascals is what you have the total pressure difference between P1 and P2. The only thing here, this density is not a constant. Z is given in terms of function of Z. Okay, so whenever density is given in terms of function of Z, in this hydrostatic law, you replace the density with this relation and you will go for the integration. Okay, but here, yes, 1082.37. Yes, even I got the same answer. Correct. Punna Tripathi, AP Tripathi, all of you, correct? Yeah, good morning, motivation learner Abhyas. Okay, fine, good. So if you see, this is how we have the certain pressure difference between the bottom and top of the chemical reactor. Okay, so let us see what is the answer. 1082.37. Yes, 1077 to 1087. So this answer is within this range. Okay, so now tell me, whenever they give you density as some function of Z, just replace this density value as this function of Z and go for the integration. But one thing you need to be very, very careful. Let us suppose in this question they told me that Z is measured from the bottom, from the top of the container. Okay, let us suppose in this question they asked me Z is measured from the top of the container. Then should I use this minus sign here? Should I use this minus sign in this hydrostatic law? Please tell me. Should I use this minus sign in the hydrostatic law if Z is measured from the top? Is the static condition important in this equation? Yes, definitely, Amit, because this equation is the derivation of this equation involves, we assume that the fluid is in static condition. Okay, clear? Yes, so when Z is measured from the top, we don't go for this minus sign. Okay, because when doing this derivations and all, we assume Z is always in the positive direction. So that's why when you take Z in the positive direction, we'll get a minus sign here. Clear? Okay, now pressure difference in positive. Yes, of course. Okay, so because of this minus sign, I have tilted these two. So P1 and P2, so P1 minus P2 comes out as this value, 1082.37 kilopascals. Okay, so is this clear to all of you? So let us go for the next question. If the atmospheric pressure at sea level is 10.143 Newton per centimeter square. Okay, so this is the atmospheric pressure, PATM. P atmosphere local. Then the density of air is 1.208 kg per meter cube. So there is some density of air also, 1.208 kg per meter cube. Now at a height of 2500 meters, means from the sea level at a height of 2500 meters, the pressure calculated by incompressible assumption is given by P1 Newton per centimeter square. At a height of 2500 meters, at the same height, the pressure calculated by isothermal assumption is given by P2 in Newton per centimeter square again. Okay, so now in that case, what is the ratio of P2 by P1 they are asking? Sorry, some comment. So please minus sign explain. Yes, definitely. Look, whenever in this hydrostatic law, when you write this equation, this minus sign is because you have taken Z in the positive direction, correct? So when you are taking Z in the positive direction, you know, in a bulk of static fluid, as you go in the positive direction of Z, means as you go towards the top, the pressure value decreases. Because let us suppose if you place your hand below 2 meters from the free surface, you will feel the weight of this 2 meters of fluid, correct? But let us suppose if you move towards height and 1 meter, then you will feel height of only 1 meter fluid. So then what happens? Obviously, as you are moving top in the positive Z direction, the pressure on your hand will actually decrease, correct? So when the pressure on your hand is actually decreasing, then in that case, this positive change in Z, means Z2 minus Z1, if it's positive, then the dP value P2 minus P1 will be negative. Okay, so that's why there is a minus sign here, because if Z is taken in the positive direction, then positive increase in Z, means if you are increasing the value of Z, the increase in pressure is negative, means the change in pressure is negative, pressure actually drops. So that's why there is this minus sign. In this case, they have again given the same condition, Z is in the upward direction. But if Z is measured in the downward direction, then what happens? As this Z increases, pressure also increases. So then dP by dZ both will have same sign. So then there won't be this minus sign. Clear? So please type in the chat box. Is this clear to you? Okay. Now let us, Amit, I hope I have cleared your question. Okay. Pressure 2 decreasing due to increasing the Z. Yes, of course. That's the reason why there is a minus sign there. Okay. Now coming to this question, we have read this question. So in one case, they have assumed the air to be incompressible fluid. What is the meaning of incompressible fluid? The density variations in Z is generally very small. I mean, this density variations in air is very small. So that's why they have assumed that this density is remaining constant in the first case. In the second case, they are taking pressure is calculated by isothermal compressible fluid assumption. Okay, then this pressure is given by P2. Then the ratio of P2 by P1. So first, let us go for this P1 calculation. P1 calculation. Now, try to observe here carefully. This is sea level, for example. So you have this is sea level and this is some height of 2500 meters. So Z1 is equal to 0, Z2 is equal to 2500 meters, for example. So here the pressure is P1, here the pressure is P2, for example. Okay. Now in this case, we are approximating the fluid to be incompressible. If you do incompressible assumption, then if this difference between these two coordinates, okay, so the difference between these two coordinates in terms of Z is 2500 meters, then you know this P2 minus P1 minus P2, P1 minus P2 is how much? P1 minus P2 is density of the fluid times G into Z2 minus Z1, because it is just linear variation. So in dP by dZ is equal to minus OG. Rho is constant, G is constant. So definitely this P2 minus P1 will be minus OFG of Z2 minus Z1. So P1 minus P2. This is the higher pressure. So this value minus this value gives you density of the fluid times G into Z2 minus Z1. Now let us calculate. This implies P2 is equal to P1 minus density of the fluid times G into Z2 minus Z1. Now let us compare this. P2 is equal to P1. P1 is the pressure at the atmosphere. So P1 is given 10 point something. So how much? 10.143 newtons per centimeter square. 10.143 newtons per centimeter square. Now try to understand one thing carefully. Look, we need the ratio P2 by P1. They are asking P1 in newtons per centimeter square, P2 also in newtons per centimeter square. Try to understand one thing. Can I keep these two in Newton per meter square? Means if I evaluate P1 in Newton per meter square and P2 also in Newton per meter square, and if I take the ratio, will the ratio be same as this ratio? Because the difference is only in units. So units conversions gets cancelled out. So let us evaluate P1, P2 in Newton per meter square. So this is equal to how many Newton per meter square? 101.43 into 10 to the power 5. You know, this is basically 10 to the power minus 4 comes out here. So if you multiply that, 10 cube. Okay, so 10 cube pascals. Okay, so 101.43 into 10 cube pascals actually. Okay, so 101.35 kilopascal. So 101.43 they have given. 101.43 into 10 cube minus density of air in kg per meter cube, 1.208 kg per meter cube. So 1.208 into 9.81 into Z2 minus Z1. This difference is 2500 meters. So this difference is 2500 meters. So if you simplify, your answer is going to be in pascals, Newton per meter square. Let us simplify this value. 101.43 into 1000. Okay, so this is the value minus this complete value. So minus 1.208 into 1.208 times 9.81 into 2500. Okay, so if you simplify, 71.803.8 71,803.8 pascals, these many pascals. So this is 71.804 kilopascals. So this is the value of P2 when you make this isothermal, this incompressible assumption, correct? So 71.80 kilopascals. Okay, 71.80. Now let us calculate P2 using the isothermal P2 calculation. So let us calculate this P2 calculation. So here we are assuming isothermal calculation. So in case of an isothermal fluid, you know, you have dP by P is equal to minus G by RT times dZ. Correct? This is the relation we have. So R is the characteristic gas constant, of course. So our value of air is 0.287 kilojoule per kg. So joule per, sorry, or you can write 287 joule per kg Kelvin directly. 287 287 joule per kg Kelvin. Okay, so 287 joule per kg Kelvin is the characteristic gas constant value, and T normally it's given, some T value is given, nothing temperature is given. So let us take by default what temperature we will take. We shall take 273 Kelvin as usual. So 273 Kelvin let us take, okay, by default. So 273 Kelvin. Now if you take 273 Kelvin and if you do the integration, correct, can I take 273 Kelvin? Please tell me. Because STP conditions, if you take temperature is 0 degrees Celsius, which is 273 Kelvin, and pressure is this 101.325 kilopascals on an average. So nothing is mentioned. So let us take the standard values, standard temperature and pressure values are nothing but these values. Okay. So now if you take this, correct, we can take this. Now if you take this, then T is equal to 273 Kelvin. Of course, 0.15 is also there if you want to use that Kelvin. Okay. Now if you integrate this, integral P1 to P2 dP by P is equal to minus G by RT, this is a constant, times integral Z1 to Z2 dz. So this is what you have. Now if you simplify this, ln P2 by P1, ln P2 by P1 is equal to minus G by RT times Z2 minus Z1, which is 2500. So this implies your P2 is equal to P1 times of e to the power minus G by RT times 2500. So let us calculate this value. What is this value? P2 is equal to P1. P1 we have converted 101.43, 101.43 into 10 cube into e to the power minus 9.81 divided by R value 287, temperature 273.15 multiplied with 2500. So the answer is going to be these many kilopascals. Okay, so these many pascals actually. Okay, so pascals, so we'll convert into some kilopascals, the conversion units basically. Okay, so now let us do this calculation. E to the power, so first of all let us do this, let us save this value. Now if you see 9.81 into 2500, 9.81 into 2500, so this value divided by 287 into 273.15, 287 into 273.15. so if you solve this, we have this value. So exponential of this value is 0.73136 into 101.43 into 101.43 into 1000, of course. So these many pascal, 74,182.35, 74,182.35, so which means 74.182 kilopascal. So this is the value of pressure at a height of 2500 meters if you use this isothermal compressible fluid calculations, and here this is the pressure if you use a linear incompressible assumptions. Okay, so they are asking you the ratio of this pressure to this pressure, correct? Set P in the second case divided by P in the first case. So what is P in the second case, which is nothing but this value divided by P in the first case. We have already stored the value, so 1.03312, 1.03312. so P in the second case by P in the first case is equal to 1.033, 1.033. okay, so 1.033 is in between 1.01 and 1.08. okay, yes, 1.033. okay, Vishal, you got some different answer. 1.05 you got. Maybe you might have taken 20 degrees Celsius NTP conditions, normal temperature pressure conditions, correct? So whenever nothing is given, you can take standard temperature pressures by default. Okay, so is this clear to all of you? Yeah, 1.033. okay, so this is how we can calculate this pressures, which is 1.033 is the ratio of pressure evaluated at 2500 meters height using this isothermal compressible assumption, and here also we have this pressure calculated using isothermal assumption. So that's why these two cases will actually give you P2 by P1. Fine. So please type in the chat box, is this clear to all of you? Yeah, I'm happy that many of you have got the correct answers. Good. Okay, so 74.182 kilopascals and this is 71.804 kilopascals. So the ratio if you take of these two quantities 1.033, which is in this value. Okay, now let's go for the next question. So did you all like these kind of questions? I think that I'm definitely sure you might not have seen this type of questions in PYQs and all, correct? So definitely I'm telling you, here we'll solve new questions and definitely we are going to deal the questions in such a way that the knowledge that you get when solving all these questions is more than enough to solve all your actual GATE 2023 questions. Okay, clear? So let's go for the next question. Okay, so let's go for the next question. So for the system shown in the figure, the air pressure PA in kilopascals for which pressure at N is 1/4 of that at M is dash. Okay, so they are asking you, there is this device basically. So here you see there are 2 points, N which is given here and also M. These are the 2 points, means at the bottom of the containers. Okay, so at the bottom of the containers you have 2 points. Now they are asking you the air pressure PA in kilopascals for which the pressure at location N is 1/4 of the pressure at location M basically. Okay, so let us see. Pn is equal to 1/4 of that at Pm. So let us see what is the pressure at location N. Pressure at location N is equal to, how much is the pressure? The pressure at this location is nothing but pressure due to this air plus pressure due to this water column, 50 centimeters height water column. I think we have made some DTPs have done some error, so this is till this 50. Okay, this is not required. Okay, there is some typing or some diagram formatting mistakes, but 50 centimeters is this total 50 centimeters of water. Okay, now let us see, if you want to calculate the pressure head at this location N, this pressure head at this location N is equal to pressure at this location plus the total pressure due to this water column of 50 centimeters. Correct? So Pn is equal to pressure at this location Pa plus pressure due to this 50 centimeters water column. So this is density of water times G into 50 centimeters in meters, 0.5 meters. This is what you have. Similarly, pressure at location M is how much? Pressure at location A means pressure of this air A, pressure of this air plus pressure due to this water column plus pressure due to this mercury column which is filled till this point. Okay, so pressure due to this mercury column. Now let us see here. Pressure due to this mercury column. Now what is the pressure due to this water column? This total height is 50 and this is 20. So this 30 centimeters, if you see, this 30 centimeters is due to this water column. Okay, so density of water times G into 0.3 plus pressure due to this mercury column is nothing but 20 centimeters. So density of mercury times G into 0.2 meters. Now this Pn and Pm are connected by this equation. Correct? So simply by applying hydrostatic law we can get this. So Pn is equal to 1/4 times of Pm. So this implies Pn is equal to 1/4 times of this Pm. So this implies Pn, which is Pa plus OWG 0.5 OWG 0.5 is equal to 1/4 times of Pm, which is Pa plus OW times 0.G into 0.3 plus OHG times G into 0.2. Now what are the values given for density of water and density of mercury? Let us say here. So if you see, it's nothing is mentioned, so you can take by default density of water is 1000 and density of mercury is 13,600 kg per meter cube. Let us take these values. Density of water is equal to 1000 kg per meter cube and density of mercury is equal to 13,600 kg per meter cube. So if you do these calculations, so you know 4 times of Pa, which is 4 Pa plus 4 times of 0.5, 2, so 2 times of OW into G. This is equal to Pa plus OW times G into 0.3 plus density of mercury times G into 0.2 actually here. Okay, so density of mercury times G into 0.2. So if you shift this Pa to the left side, you have 3 times of Pa is equal to density of mercury times G into 0.2 plus density of water into G 0.3 minus 2. It will be minus 1.7. So minus 1.7. This is the answer we are going to get. So let us substitute the values. So Pa is equal to 1/3 times of density of mercury 13,000. What is the unit they are asking you? Kilopascals. Okay, so first of all let us calculate in pascals, no issue, into 9.81 into 0.2 plus density of water, which is 1000 times G 9.81 into minus 1.7. So these many pascals is what you will get for the value of PA. Okay, so let us calculate this. 13,600 into 9.81 into 13,600 9.81 into 0.2. So into 0.2. So this value minus, because of this minus sign, there is a minus. 1000 into 9.81, 1000 into 9.81 into 1.7 into 1.7. Okay, so into 1.7. So if you simplify this value divided with 3, so divided by 3. Okay, so if you see 5.4 directly, 5.4 pascals, but the options are in kilopascals. So pressure at location A is equal to 3.335 kilopascals. 3.33 kilopascals, you can say 3.335 kilopascals is what you have here. Okay, so it's a simple question again. PA is equal to, yes, very good, 3.33. All of you are correct. So 3.33 kilopascals is the pressure at this location. Okay, so PA is equal to this 3.33. This value B is the correct answer. Clear? Simple. Write the write the pressure equations basically at those 2 points, and this relation is given to you. Pn is equal to 1/4 times of Pm. So we can go for this. Okay, simple question, right? Very simple question actually. But of course, equating pressures at 2 points could create some interest in you. That's it. Okay, so 3.335 kilopascals. Let us go for the next question quickly. So this is a manometer. For the W tube water filled manometer. So this is a W tube water filled manometer. Okay, so normally you see U tube manometers, but this is a W tube manometer. So if you see, there is some U tube, and to that U tube there is again connected one single tube. So this is a W tube manometer. Now configuration, and it's a water filled. So what is this fluid basically inside this? This is water. Okay, water filled manometer. Readings as shown. I hope these readings are not clearly visible because the diagram is small here. So AB, this dimension is given 3 centimeters and this dimension is given as 2 centimeters. Okay, so this is 2 centimeters. This is what it's given. Okay, so it is 2 centimeters, 3 centimeters and 3 centimeters and 2 centimeters. Choose the correct statement or statements. Take the atmospheric pressures as 101.3 kilopascals. Okay, so PATM is equal to 101.3 kilonewton per meter square. It's a MSQ multi-select question. Okay, so let us see. Red line MTD. What is this red line MTD? I didn't get you. Red line. So maybe somewhere here. Yes, mercury into. I hope it's clear, right? Amit, this is fine, correct? So please type in the chat box. Is this clear to you? Okay. Now let us see here. Let us go for this question. So in this question, what they are asking you, choose the correct statement and B. Okay, at A and B maybe they mean. Take the atmospheric pressure as 101.3 kilonewton per meter square. The absolute pressures at A, B is given. Okay, so let us calculate the value. Red line method use hoga. What is this red line method? I didn't know. What is this red line method? Fine. Okay, I think maybe some name given to you. Fine, look here. So this is point A and this is point B now. Okay, so how to calculate pressure at this location A? Okay, so let us suppose we are calculating the pressure at this location, for example, and this substance is actually air that is moving here. So let us suppose this is the location A and this is the location B. Okay, so location A and location B. Now first of all, if you see, this is acting like an inverted tube. It's also acting like an inverted tube manometers here. Okay, so in case of inverted tube manometers, you take the reference at the highest interface. So out of this complete inverted tube manometer on the left side of this column, the inversion has the highest interface at this location. So let us call this section XX, for example. XX. Similarly, to identify the pressure at this location, this is the highest interface. So let us take the value of this. Let us take this as y, for example. Okay, so let us take this value as y, of course. Now we need the pressures at this 2 locations. Okay, now tell me one thing. the pressure at these two locations is same, the pressure at these two locations is also same. Means if I name these points as 1, 2, 3, 4, then you know one thing, P1 is equal to P2, P1 is equal to P2, and P3 is equal to P4. P3 is equal to P4. Okay. Now let us calculate. If I calculate P2, I'll get the value of P1, and P1 is nothing but PA minus this A column pressure. But if you generally neglect these values, okay, so P1 can be written as PA minus, let us suppose if I assume this value as X, and let us suppose if I assume this value as Y, for example. Okay, if I assume this value as Y, now you know P1 is nothing but PA minus rho A GX. So P1 is equal to PA minus rho A G times of X. Similarly, here if you see, this P4 is equal to PB minus rho A GY. P4 is equal to rho A PB minus rho A GY. But generally what you can do, comparatively, coming to the water columns, the air column's pressure difference is very much small, correct? So if you take some difference of this pressure column width due to air and also due to this water, these values are very small, because you see density of air is almost density of water by 1000 of this order. Okay, so of this order, so that's why these magnitudes are almost some 1/1000 of the magnitudes due to water column. So that's why we are generally neglecting these quantities. Okay, so when you neglect these quantities, let us write neglecting air, neglecting, and here also we are neglecting the air columns. So when you neglect these air columns, neglecting, then you know P1 is same as PA. So this means pressure at location A is nothing but pressure at location P2. Similarly, pressure at location B is nothing but pressure at location 4. PB is also is equal to P4 actually here. So PA is equal to P2 and PB is equal to P4. Now, how we'll calculate pressures at location 2 and 3? Look, here we got P4 is equal to PB minus P4 is equal to P3 is equal to P4. So P3 is equal to P4. So P4 is nothing but PB minus A times G into Y. So which means you can write one thing, this P3 is nothing but this PB. Okay, so P3 is nothing but this PB. So we know this equation that P3 is equal to PB and PA is also is equal to P2. So pressure at this location 2 is nothing but pressure at this location A, and pressure at this location 3 is nothing but pressure at this location B, if you neglect the small water columns. Now, how you identify this pressure at location 2? Okay, so to identify this location pressure at this location 2, this is a manometer, and this water which is poured in this manometer is in static condition. So definitely this hydrostatic law will actually work out. Okay, so that's why if you take a section here, like this, then P2 means pressure at this location, pressure at this location will be same as pressure at this location. For example, if I call this point C, P2 value is same as this PC value. So what is PC? This atmospheric pressure plus this water column of height 3 centimeters. Okay, so that's why if you see, PC is equal to PATM plus this pressure due to this 3 centimeters water column. So P2 is equal to PATM local plus pressure head due to 3 centimeters of water column, which is 0.03 meters. Okay, so let us calculate this value of P2. So P2 is how much here? This given atmosphere, local atmospheric pressure is 101.3 kilopascals. So 101.3 into 10 cube plus density of water 10 cube into 9.81 into 0.03. So we have these many pascals as P2. So if you know in pascals, the options are in kilopascals, so you can convert this into kilopascals basically. Okay, so is this clear to all of you? So please type in the chat box, is this clear to all of you? Because we have taken this pressure equilibrium at this as per this hydrostatic law. So P2 and PC values are same. So that's why if you see, this is the calculation that we have here. Okay, so if you want to convert this into pascals, 101.3 into 1000 plus 101.3 into 1000 plus 10 cube into 9.81, 10 cube into 9.81 into 0.03. So this is the value 101,594.3. 101,594.3 pascals, which is 101.6, almost single decimal 101.6 kilopascals is the pressure at the location P2, and P2 is same as PA. So this implies this value is equal to PA, pressure at this location A. So pressure at this location A is equal to 101.6 kilopascals. Okay, next coming to PB value. How PB can be determined? PB value is same as P3. So this P3 value is again equal to, look, pressure at this location 3 is nothing but pressure at this location. So this location is having a pressure of PATM local plus 5 centimeters height due to this water column. Okay, so 5 centimeters height due to this water column. So this value is equal to PATM local plus density of water times G into 5 centimeters, which is 0.05 meters. So this implies your P3 is equal to, which is of course PB, PATM local 101.325 kilopascals plus density of fluid times G times 0.05 actually. Okay, so 0.05. So this implies your PB is equal to, let us simplify these values, 101.325 into 10 cube, 101.325 into 10 cube. Now plus, okay, 3 as they have given only 3, 101.3. okay, so let us not take this 0.25, 101.3 into 10 cube. Okay, this is the value plus 1000 into 9.81 into 5 centimeters. So into 5 centimeters. So 101.790, 101.790.5 kilopascal, these many pascals. Okay, so if you write in kilopascals, your PB value is equal to 101.8, almost 79 is 8 kilopascals, 101.8 kilopascals. So this is how in this manometer, in this W manometer, actually in this W manometer we have this 108 means 101.8 kilopascals here, and here we have 101.6 kilopascals. So absolute pressure at A is 101.6. This is correct. We have got PA is equal to 101.6. Next, so pressure at A is 204. No, this statement is wrong. Absolute pressure at B is 108.6. How much we got? 101.8. So this statement is also wrong. 101.8. Yes, this is correct. Okay, so 101.8 is correct. So A is correct statement, and at the same time D is also correct statement. Okay, so that's how A and D are correct statements for this W tube manometer. Okay, so that's why in this W tube water manometer, so it's to be very clear, it's a W tube, and at the same time the fluid is water because it's given water filled manometer. So in that manometer we have fluid as water. So that's why statements A and statement D are actually the correct options here. Okay, how we have evaluated? By simple analysis. Okay, so simple manometric analysis, we have attained these values. Air columns we have neglected because density of air is almost density of water by 1000. So the pressure columns created by air when compared to water, they can be neglected. That's the reason. Okay, is this question clear to all of you? You need to apply the concept of hydrostatics, and also you need to do these calculations little carefully by dealing with this 10 cube and all these things. Okay, so is this clear to all of you? So please type in the chat box. Is this clear to all of you? Sir, absolute and ATM pressure problem hota hai, please explain it. Okay, yes. Okay, so we'll take one time, some 2-3 minutes, and explain the difference between absolute and atmospheric pressures. Okay, Amit has some doubt, we'll spend some time. Look here, let us take it. Okay, fine, let us take some empty slide. Now normally when you measure the pressures, what happens? Crystal clear? The way you're explaining is absolutely awesome. Thank you, Bharat. Okay, Bharat, I call you Bharat. So thank you, Bharat. Now basically when you measure the pressures, what happened? Look, let us suppose if you take some container, how you determine the pressure of substance inside the container? These molecules inside the container will have certain motion. Okay, so these molecules will actually go and hit the walls of the container. So as a result you have certain pressure. Now this pressure can be measured in two types. One with respect to absolute zero. What is the meaning of absolute zero pressure? Look, vacuum, there is no molecular momentum, there is no sir, today mechanical HPCL paper, so I'm going there, sir. All the best, Vikas. I wish from bottom of my heart that you definitely clear the written test. Okay, so as if some of you are going for HPCL today, I would like to give you just one hint or one, what do you say, suggestion you can say, because I have done it myself. I have cleared HPCL last time. So I'll tell you, in HPCL technical part will be very easy. Okay, if you see 85, 85, 70, 85 and 85 questions, this is quantitative and this is technical. Means basically this is aptitude, this is technical. In technical, you might have seen some previous papers by now. In technical, what happens? Technical questions will be very easy. Just questions will be like, you just see the question, tick the answer, or at maximum you need to do some 1 or 2 line calculations, not this pi 10 cube, all these things. Okay, simple number calculations, they will get easily cancelled off. Okay, so those simple calculations will be there. So majority, if you are preparing for GATE or any competitive exam, out of this 85, maximum majority people will score definitely 75 plus. I'm telling you, you should be very careful. Okay, it's like, if you know the question, just tick it and go, that's it. Okay, and never spend so much time on any question, because there is time limit. So never spend any more time on this. Now the main game is here, quantitative aptitude, as I told you many times. So as you might have learned in many videos also, by this time you might have put some focus on quantitative aptitude, and definitely please try to make the questions in quantitative aptitude clear. Okay, questions will be easy, so just keep on solving, and definitely you will bypass the exam actually. Okay, so is this clear to you? Please focus on this quantitative part, and in exam Vikas, don't try to spend so much time on one single question. Okay, if some question is not striking out to you in some 25 to 30 seconds, then of course not calculation, I'm not talking about the solving. How to solve a question means, if by looking at the question within 25 to 30 seconds, if you're not able to you sort out how it can be solved, please skip that question and go for the next question. Okay, don't spend so much time on single question. Okay, and calculator is not allowed, as I think you might know by this time. And yes, these are things I followed when I cleared HPCL lastly. Okay, मेरे तरफ से भी best of luck dear. So Amit is also wishing you Vikas. Okay, so don't worry, you have all our wishes, so definitely you will go through. Okay, just be focused and write the exam carefully. All the best. Okay, now let's go. Fine, one of our friends asked about absolute pressure and this atmospheric pressure difference. Okay, so let us see how it talks about. Let us suppose this is the line of absolute pressure. Okay, let us suppose this is the line of absolute pressure. Means below this there is no pressure, absolute is equal to 0, means this is the pressure where complete, this is the line which corresponds to the complete 0 pressure. Okay, look, I'm telling you, if someone has doubt in how to talk about absolute pressures, gauge pressures and all, I'm giving some 2 minutes explanation, so please stay focused. This is the P absolute is equal to 0. What is the meaning of P absolute is equal to 0? Is at this location there is no molecular motion, so there is no matter. Even if there is some matter, it got settled, no molecular motion, so that is absolute 0 pressure. And every system in this universe have some pressure more than this, means of course not vacuum I'm talking, some systems if you have, like water is flowing something there, okay, some gas is getting stored, all these things they have certain pressures. Okay, so what happens if this is your atmosphere, I mean if this is your absolute, then you have your atmospheric pressure, P ATM local. So this, why I am writing local is because this sometimes it slightly changes depending upon the locations. Okay, so P ATM local at sea level, of course I'm talking about sea level. Now if you see, this P ATM local value is 101.325 kilopascals into 10 cube, these many pascals. So if you see, this is 0 pascals, means here the pressure is absolutely 0, and here the pressure is atmospheric pressure, so obviously this value should lie some above, some at some height than this 0 pascals, so that's why this atmosphere has a pressure of P ATM local. Now if you take a particular pressure, some tank, some gas tank or something, if you take, then this pressure inside the gas tank can be told in 2 ways. What are the 2 ways? First thing, absolute pressure, what I will tell you now. Let us suppose when you calculated the pressure inside the gas tank is, let us suppose you got some 200 kilopascals. Okay, some 200 kilopascals. So what you will do, first of all you draw the line 200 kilopascals somewhere here. Okay, so P gas is equal to 200 kilopascals, means 200 into 10 cube pascals. This is the actual pressure of the gas. Now when I am telling 200 into 10 cube or 200 kilopascals, I am calling it absolute. Means the absolute means we measured that value with respect to this value. Okay, so when you say absolute values are measured with respect to zero absolute pressure. Okay, so that's why if you see the absolute value of this pressure, if you see the absolute value of this pressure, is given by this reading P absolute. So P absolutes are measured with respect to zeros, absolute zeros. Now if I want to say gauge pressures, P gauge, then when I'm talking gauge or something, normally if you take any pressure gauge, those pressure gauges will actually give you the gauge values of the pressure. Means they don't talk about the absolute values. Means let us suppose if I connect, for example, if this is my water, some gas tank, if I connect a pressure gauge, now the reading which is shown in this gauge, some needle or digital meters, if you see, they actually, digital nowadays they got some software calculations and they are giving absolute, but normally the old pressure gauges, what you see, there's a dial, there's some needle in that. So if you see that, whenever you keep this pressure gauge into some medium, this value is nothing but the gauge value of this gas. What is the meaning of this gauge value? Means if you see the pressure of this reading of this reading is nothing but the difference between the actual absolute pressure of the gas inside this container minus the atmospheric pressure in which this gauge is placed. Understood? Means if you take a container like this, now if you connect a gauge to this, the gauge reading is actually not the actual value of pressure of this. This gauge reading is actually the difference between this actual pressure of the gas minus this atmospheric pressure which is here. Okay, so that's how we sometimes measure pressures with respect to atmospheres. So in such case we have this is the difference. Okay, so this is the difference between the gas pressure and the atmospheric pressure. So if you are measuring with respect to atmosphere, this is the gas pressure. So P gauge is this. Okay, so if gauge pressures are given, how you calculate absolute pressures? Absolute pressure is equal to gauge pressure plus atmospheric pressure. If you see, this is P atmosphere, so P atmosphere value is this much, so this is P atmosphere local. So if you are given gauge pressure, then the actual absolute pressure of that container is calculated using that gauge pressure plus atmospheric local. That's the reason why I'm adding this atmosphere in all these calculations. Is this clear to you? Because they're asking you absolute pressures. If they're asking you absolute pressures, you should always take this atmospheric pressure into the consideration. Is this clear to you? Okay, is this clear? Someone has asked me this question, how to talk about this absolute and gauge values, what is the difference? So did you all understand this? Fine. Now let us go for the next part. Okay, so let us go for the next parts. So let us solve this question. Okay, OHO means gauge pressure is defined actual liquid present. Yes, gauge pressure is defined with respect to the atmosphere. Okay, okay, fine. Now if you see, let us solve this question. A manometer is made of a U tube of uniform bore. Bore means some cross sectional area, so uniform bore of 0.5 centimeter square cross sectional area. Okay, with one limb. Uniform bore means uniform diameter of cross sectional areas 0.5 centimeter square, with one limb vertical, and the other limb inclined at 30 degrees to the horizontal. Both the limbs are open to atmosphere. Okay, initially it is partially filled with a manometric liquid of specific gravity 1.25. Fine. If now an additional volume of 7.5 centimeter cube of water is poured into the inclined tube, then the rise of meniscus in the left tube is dash. Very, very good question. Look, there is an inclined tube manometer. First of all, let me draw the inclined tube manometer. So let us suppose I am drawing an inclined tube manometer. So this is an inclined tube manometer, for example. Okay, if this is an inclined tube manometer, so initially what's happened, this cross sectional area of that, means the cross sectional area of the tube is given. Area of cross section is how much? Area of cross section is equal to area of cross section of the tube is 0.5 centimeter square, 0.5 centimeters square, 0.5 centimeter square. Now let us see what happened. Initially a liquid, manometric liquid of some specific gravity is poured into it. Okay, now see, if you pour a liquid of specific gravity, look, initially both these are open to atmospheres. This is atmospheric pressure, this is P ATM local, and this is also P ATM local. P ATM local. Now when you pour some manometric liquid, what happens? Can I say the manometric liquid will get settled in such a way that the meniscus on both tubes will be on a same straight line. Means if you see, the manometric fluid will get settled like this, such that the manometric fluid will get settled in the tube like this, because at this point the pressure difference due to this should be same as the pressure difference due to this vertical height. Okay, so that's why. Now let us see what happens. Tube inclination is given. Okay, so both of it and inclined at 30 degrees to the horizontal. Okay, so this inclination with the tube is 30 degrees. So this inclination is basically 30 degrees with this. Okay, so the tube inclination is 30 degrees. This inclination is 30 degrees because this theta is also needed. Okay, so first of all, why this inclined tube manometers are very effective? Because these inclined tube manometers are actually more sensitive than normal U tube manometers. What is the meaning of sensitivity? Okay, look, when you apply certain pressure difference, the deflection in this manometer will be more compared to normal U tube manometers. Okay, because in hydrostatics law, the concept behind developing this inclined tube manometers is, look, whenever you have a pressure difference, I'll ask you one question, you tell me. Okay, just simple questions I'll ask you. Let us suppose you want to measure 4 centimeters length and also you want to measure 8 centimeters length. In which case, let us suppose you have committed small error in measurements. Okay, so when you are trying to measure 4 centimeters, there is some small mistake. So छोटे से छोटे change को measure कर लेता है. Yes, definitely we'll measure. So see here, this is 4 centimeters and this is 8 centimeters. Now in which case, if you make small mistake in measurements, in which case the error will be less in calculations. Let us suppose here this 4 you have measured, you have made some 1 mm mistake in calculations, you made 3.99 centimeters. Here you made the same 1 mm mistake in calculation in measurement, so you made 7.99 centimeters. So in which case the error in the measurement is less. In which case the error in the measurement is less. Means if you are committing some mistake in the measurements, in which case the calculations will have some less error. Please tell me. You have committed same mistake of 1 mm and 1 mm in both the cases. Now in which case the error will be less, obviously in 8 centimeters, correct? So means when your measurement values are high, the mistakes that you commit will definitely give you some very small errors. So with this simple ideology, what they have done, let us suppose if I want to measure the pressure difference between these 2 points, for example, these 2 points. Okay, so in a hydrostatic case, means if let us suppose if the complete fluid is in static condition, you know, pressure changes only in P changes only in Z direction, correct? So P changes only in Z direction. Now try to understand one thing. If this location is 1, if I call this as location 1, if I call this location 2, and if I call this location 3, if I want to measure the pressure difference, of course, you see this difference, vertical difference is h between these 2 points. If I want to it, of course it's incompressible fluid density, all these things are same. So P2 minus P1 can be written as rho fluid into G into H, correct? P2 minus P1 is equal to rho fluid times G into H. Now tell me one thing, can I write P1 and P3 both are same? Yes, because those 2 points are on the same horizontal line. So in a static fluid there is no pressure variation in the horizontal direction, so P1 and P3 both are same actually. Okay, so P1 and P3 both are same. Now if I measure the distance between these 2 points, let us suppose if this is some h dash, for example. So if this angle is known to you, then definitely you know, since P3 is same as P1, P2 minus P1 is same as P3 minus, P2 minus P3. But how P2 minus P3 is calculated? P2 minus P3 is calculated with this value, rho fluid G into H dash sin theta, if this angle is theta, because if this is H dash, this vertical difference is H dash sin theta, and pressure difference only depends upon the vertical separation between the points. So even though this point got deflected towards the right, is this point 3 is towards the right, this slant length doesn't matter. The only thing that matters for the pressure difference is this vertical separation between these two. But in this vertical separation calculation, you are calculating this H dash. Theta is fixed. You know what is theta? It is fixed. So H dash measurement is definitely greater than H. So whenever you make some small mistakes, definitely the errors involved in the higher dimension values will be less. So that's why, for better accuracy and better sensitivity, we have come to the concept of inclined tube manometers than single U tube manometers. Is this concept clear? Did you all understand how the inclined tube manometers came into existence? Because these manometers are more sensitive, and at the same time, because if you apply small pressure difference, the deflection is more comparatively. So that's how your inclined tube manometers will actually give you readings with much better accuracy and of course with higher sensitivity. Is this clear to all of you? So did you all understand this clearly? Okay, clear? Great explanation, thank you. So is this clear to all of you? Now if this is clear, let us see what happens. Fine, now I am using this. Okay, simple, some basic idea. Anyhow, in your theory courses people might have taught you, but this is a problem solving course. So whenever there is some concepts, I am giving you just some crisp idea. But when I teach you this subject, maybe at some time in crash course, or maybe I don't know, when we get some chance, definitely I'll give you many such beautiful explanations like this. Okay, don't worry. Now let us see this case. So what happened? There is okay, so there is some I'm trying to draw the diagram neatly, slightly, okay, so you can understand the things. So I'm taking some time for drawing the diagram so that it looks neat. Okay, fine. Okay, so now let us suppose so if you see this, we can slightly reduce the length to this point, that this is like this, and of course there is some meniscus which is filled like this. Okay, so now this is mercury. Now whenever, so please take FM crash course, we'll take definitely. Okay, आज clear हो गया why we use inclined tube manometers. Thank you. Now see here, normally when you don't connect any pressures, if you don't connect any pressure locations at this location and this location, if both are open to atmosphere, then definitely this fluid, this manometric fluid which is poured inside, will come to such a level that the pressure difference, means if you take this value here, if you take some point here, then the pressure difference at this location, means the pressure due to this fluid column will be same as the pressure due to this fluid column of height, because for pressures to be same, because for pressures to be same, the vertical separations should be same. Okay, so the pressures come like this. The mercury levels or the manometric fluid levels get settled like this. So this is a fluid of density rho m. Now what happened? If now an additional volume of 7.5 centimeter cube of water is poured into the inclined tube manometer, then the inclined tube, then the rise of meniscus. So what happened? 7.5 centimeters water added is equal to 7.5 centimeter cube. So what they have done, they have kept some 7.5 centimeter cube water. Now tell me one thing, I am asking you one thing, you need to answer this very carefully. When I am pouring some water into this tube, will this level, means this interface, will water start increasing from this level, or when I start pouring water, because of the pressure difference, this will slightly get adjusted bottom and water will fill from this location, correct? So means if you see, what is the volume of water I have poured, what is the length of the tube that is getting filled, length of tube occupied by water, length of tube occupied by water, length of tube occupied by water is equal to volume of the water added by area of cross section of the tube, which is 7.5 centimeter cube by 0.5 actually. So this is 15 centimeters. So 15 centimeters means 0.15 meters. So this much, because 7.5 divided by half, 2 times of 7.5. So 0.15 meters means 15 centimeters of water, means 15 centimeters of length of this tube is occupied by water. But because of the pressure difference, what happens? This mercury level will slightly come down and this mercury level will slightly rise up actually. Okay, so let us see that. So let us suppose what's happening. This mercury level will slightly come down. Okay, so this mercury level will slightly come down because of the added fluid. This mercury level will slightly come down because of the added fluid. That creates some pressure difference. So this level will come down like this to some extent, and water will occupy the space. So water will occupy the space like this. So water occupies the space of some length. So water will occupy this space actually. Okay, so water will occupy this space. Water will occupy this space. Okay, so let us see. This is filled with water. Fine, water is filled here. Okay, so water is filled here like this. So this occupies some 0.15 centimeters, and here you have some mercury till this point, mercury or some manometric fluid which is present actually. Now because of this water, there will be slightly a rise in this mercury level, because here the mercury has got fall by some extent. So definitely here the same length of mercury will increase, because if fall in the mercury is x along the length of the tube, here also there is some x increase in the mercury tube, correct? So if you see, there is some slight increase in the mercury tube length, mercury in the meniscus, left meniscus. So if you see, there is some just a minute. So if you see, there is some slight increase in the meniscus. Why? There is some slight fall in the meniscus, so there is some slight increase in the meniscus. Now if you take this value, let us suppose if this fall in the mercury is x, then definitely the rise in mercury is also x, correct? Yes or no? So please type in the chat box. If this fall in the mercury is x along the length of the tube, same x length mercury will actually rise in the tube. Is this clear to all of you? We will see the hydrostatic equation and all later, but first try to understand the physics that's happening. When you pour some water, because of pressure difference, some amount of mercury will actually get lower, and here the some amount of mercury, the same length, let us suppose if x is the length of the mercury which came down, the same x length of the mercury will actually come up on the left limb. Is this clear to all of you? So please type in the chat box, is this clear to all of you? If this is clear, we'll continue the question. Okay. Now, if this is clear, then we'll continue the question. Now, let us see here. Let us see. So now this is the new interface between the mercury and water. This is the new interface. Now, if this is the new interface, let us take this new interface value. So at this new interface, tell me one thing. This slant length of fall of mercury is x. Then if I call this h, for example, if I call this difference h, can I say from this equation x is the fall of mercury, this is h, and this angle is theta, of course. Okay, so let us suppose if you form some triangle, can I say x is nothing but h divided by sine theta, or can I say h is equal to x into sine theta from this equation, correct? So h is equal to, h is the opposite side. Okay, so this angle, sorry, this angle is theta, right? Just a minute, I think we have made some thing. Yeah, so this is the horizontal. So this angle with the horizontal is theta. So which means this angle is 90 minus theta. So cos 90 minus theta is equal to h by x. H by x. So this implies sine theta is equal to h by x. So h is equal to x times of sine theta. Correct? Can I say this? H is equal to x times of this sine theta. Okay. Yes. So वो तो inclined है तो x equal कैसे है? Because whatever the volume of mercury that is coming down, same volume should increase here, and tube is of uniform diameter. So along the length of the tube, if x is the length of coming down of mercury, the same length x should rise in the meniscus. Understood? Clear? I'm repeating, normally when x is the length of the mercury that is coming down, this same amount of mercury should actually rise because the tube is actually uniform. So whenever it's a tube of uniform diameter, whatever is the length of mercury that's coming down, same should be the length of mercury that should increase. Okay, now if you see, this is the mercury manometer, this is the interface. Let us take xx. So applying hydrostatic law, applying hydrostatic law. So now let us check the things. PATM and PATM. So left limb. Let us write the pressures at these two locations. This is location 1 and this is location 2, for example. Okay. So P1 and P2 should be same. So P1 should be same as P2 because they are on the same horizontal line of a same static fluid. So this is the same fluid and this fluid is in static condition. So whenever this fluid is in static condition, this point and this point should have equal pressures because they are on the expense of same fluid. So P1 is equal to P2. So what about P1? PATM local plus density of the manometric fluid, times G into this total distance. This is x and this h is x sine theta. So x plus x sine theta. X is actually the increase in the limb. Okay, and this dimension we have calculated using this expression. So h into, so volume same height. Okay, yes. So OM manometric fluid, G into x plus x sine theta. So this should be same as, now coming to, so here if you see, this is completely water. Okay, so what is the pressure due to this water column? PATM local, of course, PATM local plus density of water into G into, what is this length we have calculated? This length occupied by this water is nothing but 0.15 meter. Length of the tube occupied by beta is 0.15. So this total length is 0.15. So slant length of 0.15 can create a pressure difference equal to 0.15 times sine theta. So the pressure difference between 2 and this 0.3 is actually given by this height of the water column. So the perpendicular height, it's not the slant height, it's the perpendicular height. So this is OWG 0.15 times sine theta. 0.15 times sine theta. So this is the equation. Did you all understand how did we generate that equation? Calculations we'll see now, only substitution and simplification is there. But first of all, did you all understand how we have generated this equation? This is the manometric hydrostatic, this is the hydrostatic law we have applied. So pressure in the left limb is equal to P1, which is equal to PATM plus pressure due to this much column of manometric fluid. So this is equal to PATM local plus pressure due to this water column, which is this OWG into 0.15 sine theta. So is this clear to all of you? This is one very good question. We need to use a lot of concepts here, you have seen. Okay, so is this clear to all of you? If this is clear, then we'll go for the calculations now. Just substituting and simplifying the things is left. Okay, so let us see here. Now if you simplify the things, PATM and PATM gets cancelled on both sides. Now if this is the only terms left, this G and G gets cancelled. So what is left over? If you simplify, oh, I think we need an empty page. I'll bring just a minute. So now let us see this equation. In this equation, rho manometric fluid times x into 1 plus sine theta is equal to density of water times 0.15 into sine theta. This is what you have. So what is x value? X is nothing but density of water by density of manometric fluid into 0.15 sine theta by 1 plus sine theta. So this is the expression for increase in the mercury level x. Okay, so this is the value of increase in the mercury level x. Now let us calculate the values. What is density of the manometric fluid? Density of the manometric fluid, okay, specific gravity is 1.25 directly given. This ratio is given, ratio of fluid to manometer, this value is given. So this is 1 by 1.25, correct? Specific gravity is 1.25. So this is inverse of specific gravity. So x is equal to 1 by 1.25 times 0.15 sine 30, 1 by 2 divided by 1 plus sine 30, which is 1 by 2. So total 3 by 2. Okay, so let us simplify the results. So if you simplify, x is equal to 0.15 by 1.25 into 1 by 2 by 3 by 2. This is the value of x. So if you simplify, 2 gets cancelled, 3 cancels 0.05 times. So x is in meters. Let us calculate what is this value. 0.05 by 1.25. 0.04 meters. 0.04 meters. So what are the units they are asking you in the question? They are asking you the question in centimeters. So if it's in centimeters, this is 4 centimeters directly. Okay, so this is 4 centimeters. Yes, 0.04 meters. So the correct answer is 4 centimeters, and the range is given from 3.9 to 4.1. Clear? So that's why this 4 is lying within that range. Clear? Understood to all of you? So please type in the chat box, is this clear to all of you? So this is 4 centimeters. Okay, it's very simple. You see, only the physical understanding of what happens takes some time. Equations, if you count this volume by area, one equation, that's it. Then this is just the simplification that I have done. Okay, so only one equation is what you need to write carefully by taking lengths and understanding the concept why when some water is added, mercury level in the right limb, it means the inclined tube is actually dropping, and the same amount of increase in the mercury. This some manometric fluid basically. Okay, so that's the important understanding here. Clear? How many of you like this question? How many of you like this question? Purnab, Amit, Tripathi, Bharat, Vishal. Did you all enjoy this question? It's not just like simple manometer, you apply some hydrostatic law. Okay, whenever some water is poured, some liquid is poured, definitely there is certain difference in the limbs. Okay, so this is what you need to understand carefully. Okay, good question, correct? Yes. So let us go for the next question. So let us go for the next question. Select the correct statement or statements. MSQ. Great. So tell me. First statement. U-tube manometers can measure both positive as well as negative pressures. Correct? Yes or no? Please tell me. Can U-tube manometers measure both positive and negative pressures? What is the meaning of negative pressures? They are talking with respect to atmosphere. Okay, atmospheric pressures. They are talking about gauge pressures and vacuum pressures. Why? There is nothing called absolute negative. If there is some molecular motion, you have certain positive pressure. If there is no molecular motion, pressure is 0. That's it. It's not like you have negative absolute values. But when they are talking about positive and negative values, they are talking about pressures which are more than atmospheric pressures, which are gauge pressures, and negative pressures means pressures which are less than atmospheric pressures, which are vacuum pressures. Is this clear to you? So tell me, can U-tube manometers measure both positive and negative pressures? Yes, they can measure, correct? Because if you see, for normally when you connect this mercury manometer like this, let us suppose if this is PATM and if this is some pressure P which is subjected. So now if P is greater than PATM, if P is greater than PATM, mercury will take a deflection like this. Means if P is greater than PATM, then this pressure will try to push the mercury column. So like this is how you actually see the mercury deflection in manometers. If P is less than PATM, let us suppose if P is less than PATM, then if you have this U-tube manometer like this, then like this, then in that case, if this is subjected to P and if this is subjected to PATM, now PATM will be more powerful, so this will push the limb bottom and here it will be rise. So you can measure both positive and negative pressures, means basically gauge and vacuum pressures using U-tube manometers. Clear? So that's how we can get this. Okay, so this statement is actually correct. U-tube manometers measure positive as well as negative pressures. Okay, now next statement. For better accuracy in measuring difference of pressures, inverted U-tube manometer is preferred. Yes or no? Tell this statement. For better accuracy in measuring difference of pressures, inverted U-tube manometer is preferred. Yes or no? Is there any advantage by taking inverted tube manometers? Okay, forget about it. I'll ask you this question. How many of you don't know the logic or the reason behind why inverted tube manometers serve better than U-tube manometers? Even if there is someone, I'll definitely spend some 2-3 minutes time and I'll explain you. Tell me, how many of you don't have this clear idea why inverted tube manometers will be better than this U-tube manometers? Tell me. Why these inverted tube manometers have better accuracy or better, they are actually better for the pressure measurement? Then please tell me. How many of you have this, not very clear? No idea, sir. Negative pressure measurement easy. Please explain. Vishal, Purnab, no idea, sir. Okay, look, I'll spend only 2 minutes of time. You will understand. Let us suppose there is a pipeline in which there is some flow that is taking place. This is a pipeline in which there is a flow that is taking place. Okay, so there is certain flow. This is location A, this is location B. Now let us suppose you have normal manometer, you have normal U-tube manometer. So this is normal U-tube manometer, and let us suppose this you have inclined tube manometer. I'm drawing some of sketches actually. This is inclined tube manometers. Now this is one normal manometer and this is inclined tube manometer. So let us suppose the mercury deflections are like this. For example, let us suppose PA is greater than PB, for example, because as you generally go there is some pressure drop. So let us suppose PA is greater than PB. Okay, so when PA is greater than PB, let us suppose this is mercury column that is present here. Okay, so let us suppose this is how you have the mercury columns. Okay, so let us suppose this is the mercury columns. So now let us suppose the deflection here in this case between these two limbs, the deflection between these two limbs is x, for example, x. This is normal fluid that is flowing and this is manometric fluid, density of manometric fluid. Now tell me one thing, out of these two fluids, which fluid have higher density? Normal fluid and also manometric fluid. Now tell me, out of these two fluids, which fluid have higher density? Manometric fluid or the normal fluid? the fluid which is actually flowing, or the manometric fluid which have higher density? Tell me, which have higher density out of these two? Which have higher density out of these two? Obviously manometric fluid have higher density, correct? So density rho m is actually greater than rho. Okay, now let us take the case of inverted tube manometer. So here, if you see, this is water, for example, let us say some water or air, anything is flowing. There is some water which is flowing. Okay, water is flowing. Now similarly in inverted tube also, if PA is high, if you try to draw an interface, like this, then definitely this water is filled here. Okay, so if you see, this won't have here, so to some extent you have this gas. So this is some manometric fluid. You have some manometric, fluid. Okay, so something like this, for example. Okay, so you have some manometric fluid like this, so that you have this interface. Now, and here you have some liquid again, because you see, you will have some liquid like this. Now if you see, the manometric fluid has shown a deflection which is equal to y. So this manometric fluid has certain deflection which is y. Now in this case, correct? Now if you apply hydrostatic law between, for this normal single U tube manometer and inverted tube manometer, so let us suppose you have done for this normal manometer, single U tube manometer. So if you see, the pressure at these two locations should be same. Pressure at this location 1 and at this location 2, they should be same. So P1 and P2, this difference is given by P1 minus P2, or P1 minus P2 is same as PA minus PB, which is equal to density of the manometric fluid into G into X, correct? Because if the manometer shows a deflection X, the pressure columns due to this water get cancelled out on both sides. So pressure at this location is equal to pressure due to this water column plus this water column. Similarly, pressure at this location is equal to pressure due to this water column plus here mercury. So if you see, let us consider density of water also. If you consider, you will get density of manometric fluid minus density of water divided into G into X. So this is what you have here. Okay, so the pressure difference between A and B is calculated using this method. Now tell me, here if this is the manometric fluid and here if it is density. Now density of the fluid. Now tell me, out of these two, which is higher now? In case of an inverted tube manometer, which density is higher, the flowing fluid or the manometric fluid? Please tell me, in this case, which fluid has higher density? Which fluid has higher density? The fluid flowing or the manometric fluid? Normal fluid, correct? The fluid actually which is flowing in the pipe has higher density, correct? Because in case of inverted tube manometers, one thing has to be very clear, normal fluid have more density now, correct? Obviously, because if you see, in an inverted tube manometer, if your manometric fluid is of higher density, then obviously the higher fluid density, the fluid with higher density will actually fall into this tube. Then it doesn't serve as a manometer anymore. It just acts as a bypass for the fluid. That's it. Okay. For this tube to function as a manometer, this manometric fluid density should be less than this density of the fluid. Okay. So that's one very, very important understanding here. Now here also, if you see PA minus PB, this value will be equal to density of the fluid minus density of manometric fluid times G into Y. This is how you get. Okay. So PA minus PB from this relation is density of fluid minus density of manometric fluid times G into Y. Here it is density of manometric minus density of fluid into G into X. Now tell me one thing, you measure the pressure using single tube manometer or you measure using inverted tube manometer. Is the pressure difference same between these 2 points? Yes or no? Because if you see, you are trying to measure pressure and the connection is between that same 2 points. Whenever the connection is between two same points, if you measure the pressure difference using a single U tube manometer or using a differential tube manometer, or you calculate using an inverted tube manometer, is the pressure same in both the cases? Yes or no? So please type in the chat box. Amit, it's very simple. Look, I'll tell you. this is inverted, correct? You know, if you try to pour two fluids, then what happens? The fluid with higher density will try to settle at the bottom, and the fluid with lighter density will be on the top, correct? Let us suppose if you pour water and kerosene together, then what happens? This kerosene will actually float on water, correct? That's how actually you see fight scenes in movies and all are shot. What they do, they'll pour some one layer of petrol or kerosene on top of some water, and they will lit the fire. So you will see some fire. If there is some emergency, definitely down there is some water. Okay, this principle in defenses is actually used. Principle of defense in densities is actually used for these principles. Okay, so now if you see, whenever if you are inverting this fluid should have higher density than this. Similarly here, this fluid should have higher density than this. Okay, that's it. Now if you see, this Pa minus Pb is same in any value. So that's the reason density of manometric fluid here M1, let us call this M1, and this is called this M2 for example. So rho M1 minus rho water times G into X. This difference will be same as rho water minus rho manometric fluid 2 times G into Y. So if you cancel out this G all sides, now try to understand one thing carefully. Normally in this manometric fluids you use mercury as the manometric fluid. So this value is around 13,600. This is 1000. This is 1000. And normally in inverted tube manometers and all, you use compressed air as manometric fluid. So when you use compressed air as manometric fluid, 1.2, almost 1.2 kg per meter cube, something like that. Now tell me, look, try to understand one thing. The accuracy of the pressure measurement depends upon the measuring. Okay, so you have seen measuring larger lengths will give you higher accuracy. Now this difference is 12,600 almost. If you neglect this 1.2, this difference is 1000, which means, can I say one thing? If 12,600 times of X is almost equal to 1000 times of Y, which means Y deflection will be 12.6 times of the deflection of X. Yes or no? Which means here if you see, the deflection for the same pressure difference in the inverted tube manometer is almost 12.6 times of what you get in a single tube, I mean this differential tube manometer. And of course you know the densities and all. In this calculation the only thing you need to do with accuracy is this Y, because these densities are fixed, gravity, acceleration due to gravity is also fixed. Similarly here also this differences densities are fixed, G is also fixed. So rather than measuring X, if you measure Y, the difference will be, means the accuracy will be much higher, because this deflection shown by this manometer, inverted tube manometer, is almost 12.6 times of the deflection that is shown in case of this YouTube single differential YouTube manometer. So that's the reason why inverted YouTube manometers give better accuracy in pressure measurements. Clear? Is this clear to all of you? Did you all understand clearly why inverted tube manometers give you better accuracy in pressure measurements? Yes or no? Type in the chat box. Clear? Did you all understand this? Why inverted tube manometers give you better accuracy as compared to normal YouTube differential manometers? Okay, and in case of this YouTube manometers, you should always go for the lowest interface of the fluid and manometric fluid for datum. In case of inverted tube manometers, you should always go for the highest interface. That's why I have taken two sections. Okay, so coming back to this statement, for better accuracy in measuring difference of pressures, inverted YouTube manometer is preferred. Yes, correct. Inclined tube manometers are more sensitive as compared to other manometers. Of course, we have seen for the same difference in pressure, inclined tube manometers show higher deflection. Okay, so this is also correct. For measuring pressure difference between two conduits, means two flows, the same flow at two different locations carrying water, inverted YouTube manometer with mercury as manometric fluid is used. First of all, try to understand this statement. Inverted YouTube manometer with mercury as manometric fluid. And what is the fluid that is flowing? These pipes are carrying water. So tell me, in this configuration, whenever the fluid flowing is water, can you use mercury here? Whenever in this combination, if fluid flowing is actually water, can you use mercury as manometric fluid? Can you use mercury as manometric fluid? Can you use mercury as your manometric fluid? Obviously, no. Because you see that fluid is of higher density, it will fall into the water. That's it. No, never. That's it. Okay. So that's why this statement D is actually a wrong statement for you. So A, B, C are the correct answers for this MSQ. A, B, C are the correct answers. Okay, so did you all understand with logics why these statements are correct now and why this statement is wrong? Because it's not like you mug up inverted tube manometers give better accuracy. You should know why they are capable, why they are much more accurate in measurements. You should know the technical things behind them. Okay, that's the reasons. Clear? Now I hope you have some logical explanation for all these three reasons, especially these two. Correct? Now fine, let's go for the next question. We have spent some time. So this is one manometer again. Water flows upward in a let us see here. Okay, you understood very well. Good, I'm happy then. Okay, so see here, water flows upward in a pipe slanted at 30 degrees. So this pipe is slanted at 30 degrees. If this angle is 30, with horizontal also this angle is 30. Okay, because you see transversal and angles on alternative sides. The mercury manometer width 12 centimeters. So this deflection read by mercury manometer is 12 centimeters. This H value is 12 centimeters. So this is mercury and this is 2 meters. So this length, this width is actually 2 meters. Okay, this is 2 meters. The absolute pressure difference between 1 and 2 in the pipes is dash. So P1 minus P2 magnitude. What is the magnitude of P1 minus P2? This is what they're asking you. Okay, so P1 minus P2. What is the difference in the pressure? Okay, so let us see here. Let us see. So if you want pressure differences between P1 and P2, so let us take equilibrium between these points, because this is a straight manometer, it's not inverted. So when this is a direct manometer, you go for the lowest interface of fluid and manometric fluid. Here is one interface, here is one interface. Out of these two, this is lowest. So let us take this as the section XX. So this is the section XX. Okay, XX here, X and X. So this point is 0.2. So now P1 and P2 should be same, because this fluid is in static condition. Okay, this is flowing, but this fluid is in static condition. So it is a same fluid expense. So definitely P2 and P1 should be same. So P1 is equal to P2. Let us see here. P1 is equal to P2. So this implies P1 is equal to P2. So now what is P1? Let us suppose if this is the location of means basically if you say, for example, there is no radial variation of pressure, means normally if the pressure at this location is P1, at this location is also P1 actually. Okay, normally you will come to know later when I talk about viscous flows of incompressible fluids through pipes and all, you will see this relation. Normally this dou P by dou R will be very small. This is 0 almost. Okay, so there won't be any pressure variations with respect to radius. Okay, so if you see, if pressure P1 at the center of this pipeline is P1, pressure at this location is also P1. Similarly, if this is P2 here, and this is also, it is P2. Pressure at this location 2. Okay, so this is P1. Now let us see here, what is the pressure at this location 1? Location at this location okay, 1, 2 I have already used. So let us take A and B for example. Okay, so capital A and capital B. Let us take capital A and capital B here, because 1, 2 we are using here. Okay, so that's why. So capital A and capital B. So PA is equal to PB. Let us write PA is equal to PB. Now what is PA? P1 plus pressure due to this water column. This water column is of height H. So density of water times G into H. Density of water times G into H. So this is equal to P2. So what is this P2? P2 is this PB. PB is how much? P2 plus this pressure P2 plus pressure due to this water column plus pressure due to this mercury column. So we need to identify what is this dimension X, let us say, because we need the pressure due to this water column X. So P2 plus rho water column GX plus rho mercury GH. This is what you have. Okay, so rho mercury GH. This method used as a red line method. I don't know what is this a red line method and what is this a red line, but okay, anyhow, you are talking about some method which I am using. Okay, good. So now if you see, P1 is equal to this quantities. Now what is X? X is not known. X is the only quantity which you don't know. But to identify X, we know something. Look, this difference is given to be 2 meters and this angle is 30. So this dimension is 2 meters and this angle is 30. So if you want to calculate this vertical height X, so X is equal to 2 times of sine 30. sorry, tan 30, correct? Because tan 30, so this is vertical dimension, so tan 30. So which means x is equal to 2 by square root of 3. That's it. Okay. So 2 by square root of 3 is the dimension of this help. Okay. Someone help. Teen tech. Okay, fine. Okay. So see here. This is x actually. Okay. So this is your dimension x and this is your 2. So x is 2 times of tan 30, which is 2 by square root of 3. Look here. Let us substitute. P1 minus P2 is equal to density of mercury minus density of water times GH plus density of water times G into this x is 2 by square root of 3. That's it. Okay. So let us simplify these values. P1 minus P2 is equal to, how much is this value? Density of mercury minus density of water. Okay. Values are not given. So let us take by default 13,600 minus 1000 times 9.81 times this value h. H is how much? The deflection shown is 12 centimeters. So 0.12 meters plus the density of water, which is 1000 into 9.81 into 2 by square root of 3. These many pascals. This is in pascals because everything we have substituted in SI units. So pascals, the answer should be in kilopascals. Okay. First of all, let us calculate in pascals. Then you can see kilopascals. Okay. So now let us see here. 13,600 minus 1000, so 12,600. 12,600 into 9.81. Oh, something got happened. Look, 12,600 into 9.81 into 0.12. 0.12 plus density of fluid into 9.81. Density of fluid into 9.81 into 2 by square root of 3. Okay, so if you simplify this, 26160.33. 26160.33 pascals. So this implies your P1 minus P2 value, the pressure difference, is equal to 26.16 kilopascals. Okay, so this is 26.16 kilopascals is what you have here. Okay, so 26.16 kilopascals. So option A is undoubtedly the correct answer. Okay, so what is the answer given? Yeah, 26.16. Yeah, option A is the correct answer. Okay, some exams are posing and I'm confused how to start fluid mechanics. Before starting fluid mechanics, what basic concept I should study from class 12 or class 11 before moving to fluid mechanics? Just slightly focus on some basic mechanics principles. Okay, engineering mechanics course will definitely help you out once you are thorough with this engineering mechanics course, because later in hydrostatic forces and all we'll use some moment of inertias. Okay, in fluid dynamics we use Newton's law. Okay, moment of angular momentum equations, all these things. Okay, so that's why you go for some basic engineering mechanics course. Okay, engineering mechanics you do, then you can go for this what do you say, fluid mechanics. Okay, size में inclination affect नहीं करेगा. Yes, inclination definitely affects. That's why this tan 30 degrees came into the picture. Okay, because of that inclination only we have taken this tan 30 degrees, and there is some excess elevation. If the pipe is straight, there is no excess column. Okay, this excess column is because of the inclination of the pipe, and we have considered the pressure difference due to inclination, which means this pipe inclination effect came into the picture. Okay, clear? So please type in the chat box, is this clear to you? (26.16) is correct answer. Of course, if you simplify the result, you will get 26.16. The only thing is the pipe is inclined, so you have certain height. So let us go for the next question quickly. A multi-tube manometer using water and mercury is used. The diagram became very light, correct? Is it visible? Okay, so let us see. So let us anyhow see this. Okay, so 10. I think we have 3 more questions. Okay, fine. Let us see. A multi-tube manometer using water and mercury is used to measure the pressure of air in a vessel as shown in the figure. For the given values of heights h1, h2, h3, h4, h5 and h6, the gauge pressure in the vessel is dash. So whenever they're talking about gauge pressure, let us go for this PATM. With respect to PATM means, let us suppose if the pressure of air in this tank is PA, if here the pressure is PATM local, then they are asking you what is the value of PA minus PATM local. That's what they are asking you. Okay, this is what they are asking you in is dash. The gauge pressure in the vessel is dash kilopascals. I think units were not mentioned maybe, so kilopascals. Let us see. Okay, so kilopascals. Let us see here. No visibility. Yes, diagram is not visible, correct? So let me draw the diagram once on this trace. It is very light actually, but I'll try to put the dimensions. The diagram became very light, so okay. So in this, there is this level, which is, of course, if you see, this is water, the fluid here is water. The diagram came very light. Okay, so maybe something H2 is still this level. Now here you have mercury again. This height is H1, this height is H1. You have air here, so in this you have air. This is mercury, this is mercury is given, this is mercury till this point. Now this is H4, no, H3, this is H3, this height is H3. Okay, now this height is H5 again, so this height is H4, this is H4. Okay, and this is given H5, small gap H5, and this difference is given, this top to this value, this is given H6, this is 0.0, this is given. Okay, so this is the diagram basically given. So at all, above all the interfaces you have water, and here you have mercuries, okay, at some locations. So this is how the manometer is given. Okay, now I hope it's better than previous. Really, now let us see here. Let us start a location here, and let us try to reach this point A, for example. Okay, so let us see. PATM local is the pressure initially. Look, this is a very good question, so let us try to understand, and let us try to write carefully here. Okay, so let us try to write carefully. So we have started at PATM, and the pressure at this location and this location is same, because we are neglecting the air column. Okay, so air column is neglected, so the pressure at these two locations is same. So let us suppose here also the pressure is PATM. So PATM minus, for this manometer, this is the interface. Okay, so for this manometer, this is the interface. Okay, for this tube, this is the interface of liquids with maximum and minimum intensities. So now if you see here, if you see, this is H6 plus this small difference is H5. So there is mercury till this level, correct? So till this particular point there is mercury. So till this particular point there is mercury. So pressure difference from here to here is plus density of mercury times G into H6 plus H5. So plus density of mercury times G into H5 plus H6 is what you have. So density of mercury times G into H5 plus H6 till this point. Now here to here the fluid is same, it is mercury, so definitely this difference gets cancelled out. Okay, now what happens next? If you see, till here the fluid is water. Okay, so till here the fluid is actually water, so minus density times G into H5. Okay, so minus rho W G into H5 minus, if you see, this water is continuing till here. So if you see, for this inverted U-tube manometer, here we have the interface again. Okay, so this is the top interface. So if you see, this dimension is H4 and this dimension is H5. So from this point, if you travel upwards towards this point, minus water times density into H4 plus H5. So minus water times density of water times G into this H5 plus H4, H5 plus H4. Now again, from this location to this location it is completely water, so the pressure heads gets cancelled on both sides. Now from this location again to this location it is H4, this is mercury, correct? So if you see, this is mercury here, this is H4 location, it is mercury. Okay, so minus rho W G H4 this is again plus, correct? So it is coming, we are measuring again in the downward direction. So plus density of mercury times G into H4 plus density of mercury times G into H4. Okay, so density of mercury times G into H4 minus again mercury times G into H3, because this pressure head is cancelled. So again you are going in the positive Z direction. So minus density of mercury times G into H3. So minus density of mercury times G into H3. So you again reached this point. Now if you see, there is water again with this distance of H3 minus H2. So minus OW times G into H2 minus H3 is this length. So minus density times water into G times of H2 minus H3. So H2 minus H3 is basically this gap. So if you see, for this inverted tube manometer, this is the interface. So if you see, the water column has to be subtracted. So H2 minus H3 is the water column. So minus this water column pressure has also to be subtracted. So this is came. Now if you see, this is the mercury again interface. So at this interface, if you take, at this interface if you take density of mercury times G into H2 is in the again downward direction. So plus density of mercury plus density of mercury times G into H2. Okay, so plus again density of mercury times G into H2, then this is again mercury, so no issue, minus density of times air into H1. So minus density of air times G into H1. So we finally reached this point. So the pressure at these 2 points is same. So this value is nothing but same as PA. So look here, whenever you are writing the pressure difference in the upward direction, means whenever you are writing this pressure when you are going up, those pressure columns will be negative, and when you are coming down again, those pressure columns will be positive, because decrease in the direction of Z will actually give you a positive pressure change, increase in the direction of Z will actually give you a minus pressure change. So that's why if you see, this is how we have this equation. Now let us simplify this equation. If you shift this PATM to the other side, PA minus PATM local is equal to, what are the terms that are left? Density and water terms. Let us see. OHG times H5 plus H6 plus H4 minus H3 plus H2. These are the density of the mercury terms, minus density of water times G into H5 plus H4, H5 plus H4, then plus H2 minus H3 plus H2 minus H3. That's it. Okay, so these are the terms. Okay, let us neglect this air column. This column can be generally neglected because density of air is very much less as compared to density of water and mercury. So these are the values that you have for PA minus PATM. Okay, so if you simplify, PA minus PATM local is equal to 13,600 times of H5 plus H6, H5 plus H6 0.6 plus H4 plus H2, H4 plus H2, so 0.5 plus 0.7, 1.2 minus H3 value, which is, H3 value is how much? 0.3, 0.3 minus 1000 times G of, here also there is G, H5 plus H4 plus H2, H5 0.1 plus H4 0.8 plus H2 0.8 plus 0.5 1.3 minus H3. So what is H3 value? 0.3. Okay, so 0.3. If you do this calculation, this is 1, and what about this 1.8 minus 0.3? 1.5. So 13,600 into 1.5 minus 1 into 1, so that is 1 anyhow. So this value multiplied with the G, these many pascals. Okay, so into 1000 is there, correct? So 1000 into 1, 1000 into 1. So if you see, these many times G, these many pascals. Okay, so these many pascals. So 13,600 into 1.5 minus 1000. So if you simplify, this is the value multiplied by 9.81. So 190,314 pascals, which is 190.314 kilopascals. 190.314 kilopascals. Okay, fine. So see here, this is 190.314 kilopascals, because you can see starting from this location, come towards this location, go see, this is a straight manometer, so go for the least interface. Again, this is an inverted tube manometer, go for the highest interface. Again, this is a normal manometer, so come for the lowest interface. Inverted tube, go for highest. Normal tube, go for lowest. So if you see, if you travel in this direction, so this is increase in the pressure, minus this is decrease in the pressure, plus this is increase in the pressure, minus this is again decrease, plus increase, minus decrease. That's it. If you go in this fashion, you will get the answer in a single line like this. Okay, of course this is just simplification. So 190.314 kilopascals, 190.314 is within this range. Okay, so is this clear to all of you? You need to be very clear with the hydrostatic principles. So you have traveled along the positive and negative, differences of pressure. That's it. And finally we reached this point A. Clear? Okay, now let us go for the next question. So ninth, how many questions are left? Because we have only 2 more questions are left, simple questions. See here, for the configuration shown below, the value of H in meters is dash. Where is H actually? Here is H. Okay, so interface is given, water and mercury interface. So water and mercury interface is given. So if you see, this is completely mercury. So pressures at these 2 locations, 1 and 2, should be same. So right, P1 is equal to P2 as per hydrostatic law. So what is P1? P1 is P ATM local, P ATM local, plus this is oil of height 0.3. So density of oil times G into 0.3 is the pressure, plus density of water times G into 0.4. Okay, so density of water times G into 0.4. This is equal to pressure due to this location. So which is P ATM local, P ATM local, plus density of mercury into G into what is this height of the mercury column? This height is nothing but, look, this height from here to here is 0.7. So from here to here also it should be 0.7, but this is given H. So this small height is nothing but 0.7 minus H is the value. Okay, you need to apply little calculation. So 0.7 minus H. So 0.7 minus H. So if you simplify the results, P ATM local gets cancelled off. And what about H? G also gets cancelled in all the terms after cancellation of P ATM local. So 0.3 times density of oil plus 0.4 times density of water divided by 0.7 times, okay, is equal divided by density of mercury, or you can write is equal to density of mercury times 0.7 minus H. This is the value of H in meters. So let us calculate the value of H in meters. What is density of oil? 880 kg per meter cube. Density of mercury 13,550 kg per meter cube. So if you simplify, 0.3 times of 880, 0.3 times of 880, 0.3 times of 880 is this, plus 0.4 times of density of water, say 400 for example, plus 400, plus 400, plus 400. This value divided with density of mercury 13,550. So this is the value 0.49. So 0.49 is equal to 0.7 minus H. So what is H? 0.7 minus this value. So minus of this plus 0.7. So if you see 0.65099. So H is equal to 0.65099 meters. Okay. So H value is equal to 0.65099 meters. So which is nothing but 0.651, which is in option C. Okay. 0.65099 meters. So which is 0.651 meters. Clear? Okay. Let's solve one last question before we leave. So one last question we can solve. An inverted differential tube manometer, it's a simple question, is connected to 2 pipes A and B as shown in the figure, which convey water. The fluid is manometer is of oil of specific gravity is 0.8. So this density is actually equal to 800 kg per meter cube. If you take this as water, then the pressure difference between points A and A, PB minus PA. Okay, so if you take this datum, this is the highest interface. So if you take this as the datum for example, then you have these locations, at these locations 1 and 2. So P1 is equal to P2. P1 is equal to P2. So what is P1 at this location? So if this is A, location A, so PA is here also, it is PA. So P1 is actually PA minus this water column height. So P1 is equal to PA minus this water column pressure, which is density of water times G into 0.3. Now what is P2? P2 is equal to, at this location the pressure is PB, because here also the pressure is B. So PB minus this water column height, which is 0.3. So PB minus water column of height 0.3 minus this pressure due to this oil column. So what is this total oil column length? This is 20 plus 30. So obviously this has to be 20 centimeters. Okay. So this is 20 centimeters. So minus density of oil times G into 0.2 actually. So if you equate these two, P1 and P2 are same. So if you equate these two, sorry, PPT mil jayegi. Yes, definitely you will get the PPTs. Okay. In the Infinity app. So see here. PB minus OW. So if P1 and P2 both are same, so P1 is equal to P2. P1 is equal to P2. So this implies P1 is how much? PA minus density of water times G into 0.3. This is equal to PB minus density of water times 0.3 minus density of this oil times G into 0.2 is what you have. Cancel these two terms. So PB minus PA value, or PA minus PB, is nothing but density of oil times G into 0.2. So density of oil is given to you, which is 0.8 is the specific gravity. So 800, G is 9.81 into 0.2. So 0 and this 0 can cancel. So 160 times of 9.81 pascals. So if you check 160 into 9.81, 160 into 9.81. So if you simplify, 1569.6, 1569.6 pascals. Okay. And what are the units they are asking you in? Newton per meter square. So they are also asking you in pascals. So 1569.6. So 1569.6 pascals. Okay. So 1569 is within the range of this question. Okay. Yes, 1.569 kilopascals. Of course, 1.1569 pascals is also same here. Clear? So that's how. Okay. So thank you. That's it. Okay. So some 10 to 11 questions, I think 10 to 11 or some questions, 11 questions. But of course, these 11 questions are very good questions, and we have used the principles of hydrostatic law and manometers. We have learned some important understandings, why inclined tube manometers are better, why inverted tube manometers are much better. We have talked about all these things, and we used all our concepts in solving this. We have solved all these questions basically. Okay. So there is the mechanical telegram discussion group, so you can definitely join that so that if you have any doubts or issues regarding the class or anything, you can just connect over there. Okay. So are you all liking the questions? These questions we have solved. If you see, we have solved some very nice questions in between. Okay. So this, for example, we have to take a lot of curves to get that location. Okay. Then we have seen why this theoretically, these explanations and all we have given. Okay. Then this inclined tube manometer is again one very good question, where you pour some water and all. Okay. So this W tube manometer again. Okay. And we have seen this this second question, basically pressure inside the reactor, chemical reactor we have seen. So we have seen all these kind of questions actually, and it's not like they are not the common questions that come in GATE exam directly, but to solve these questions we need all the concepts which are more required than which are actually more than required for solving GATE questions. Okay. So once you solve these questions in this Abhyas batch, definitely you can definitely get all this questions in GATE examination. Okay. And also, since this content is for free, so you can definitely basically when you are doing combined studies and all, definitely this will help you out to your friends as well. Okay. So clear? So I hope it's fine to all of you, right? Okay. So any doubts? You can, if you have some doubts, you can talk to me, or else we will wind up this session because we have already crossed the time by 8 minutes. So if you have any doubts, you can talk to me. If you have any doubts, you can talk to me, or else if it's fine, then we will close this session. So please type in the chat box. Is this clear to all of you? So hydrostatic force questions we'll do in next lecture. Today I'm going to post some short video telling you about the complete detail of this fluid mechanics batch. Okay. We'll make some short video, some 2-3 minutes video, and we'll upload so that you will come to know what are the complete you know, what are the complete basically topics or chapters you see that we deal in each day of this Abhyas course. Total 10 lectures I will take. 2 lectures I have already taken yesterday for fluid and its properties, today pressure and its measurements. Okay, so we'll give you a detailed schedule today. Okay, fine then. Thank you all. I hope you liked the session, so you enjoyed it. So that's it. Okay, namaste. Thank you. Thank you all. Okay, I'm ending the stream then. Thank you all. Thank you.